What's the difference between Os.Urandom and random? On the random module Python page, link here, there is this warning. Warning, the pseudorandom generators of this module should not be used for security purposes. Use Os.Urandom or SystemRandom if you require a cryptographically secure pseudorandom number generator. So what's the difference between Os.Urandom and random? Is one closer to a true random than the other? Would the secure random be overkill in non-cryptographic instances? Are there any other random modules in Python?
You can read up on the distinction of cryptographically secure RNG in this fantastic answer over at crypto.say. The main distinction between random and the system RNG like Urandom is one of use cases. Random implements deterministic PRNGs. There are scenarios where you want exactly those. For instance, when you have an algorithm with a random element which you want to test, and you need those tests to be repeatable. In that case you want a deterministic PRNG which you can seed. Urandom on the other hand cannot be seeded and draws its source of entropy from many unpredictable sources, making it more random. True random is something else yet, and you'd need a physical source of randomness like something that measures atomic decay, that is truly random in the physical sense, but usually overkill for most applications.
So what's the difference between Os.Urandom and random? Random itself is predicable. That means that given the same seed, the sequence of numbers generated by random is the same. Take a look at this question for a better explanation. This question also illustrates that random isn't really random. This is generally the case for most programming languages. The generation of random numbers is not truly random. You can use these numbers when cryptographic security is not a concern, or if you want the same pattern of numbers to be generated. Is one closer to a true random than the other? Not sure how to answer this question because truly random numbers cannot be generated. Take a look at this article or this question for more information. Since random generates a repeatable pattern, I would say that Os.Urandom is certainly more random. Would the secure random be overkill in non-cryptographic instances? I wrote the following functions and there doesn't appear to be a huge time difference. However, if you don't need cryptographically secure numbers, it doesn't really make sense to use Os.Urandom. Again, it comes down to the use case. Do you want a repeatable pattern? How random do you want your numbers, etc.? Results. Are there any other random modules in Python? Python 3.6 introduces the new secrets module. Random implements a pseudo-random number generator. Knowing the algorithm and the parameters, we can predict the generated sequence. At the end of the text is a possible implementation of a linear pseudo-random generator in Python that shows the generator can be a simple linear function. Os.Urandom uses system entropy sources to have better random generation. Entropy sources are something that we cannot predict, like asynchronous events. For instance, the frequency that we hit the keyboard keys cannot be predicted. Interrupts from other devices can also be unpredictable. In the random module there is a class, SystemRandom, which uses Os.Urandom to generate random numbers. Actually, it cannot be proven if a given sequence is random or not. Andrei Kolmogorov worked this out extensively around 1960s. One can think that a sequence is random when the rules to obtain the sequence, in any given language, are larger than the sequence itself. Take for instance the following sequence, which seems random. 264 octillion 338 septillion 327 sextillion 950 quintillion 288 quadrillion 419 trillion 716 billion 939 million 937,510. However, we can represent it also as pi digits 21 to 50. Since we found a way to represent the sequence smaller than the sequence itself, the sequence is not random. We could even think of a more compact language to represent it, say pi 21, 50. Or yet another. But the smaller rules, in the most compact language, or the smaller algorithm, if you will, to generate the sequence may never be found, even if it exists. This finding depends only on human intelligence, which is not absolute. There might be a definitive way to prove if a sequence is random, but we will only know it when someone finds it. Or maybe there is no way to prove if randomness even exists. An implementation of an LCG, linear congruent generator, in Python can be